All right, welcome guys. We're going to be talking today about common ions. This is the last thing that's going to be for this test that's coming up. We're going to start the lectures for exam 2 before the test happens. So this is the last part of it. I have opened the test an additional day because I didn't get this up the day that it should have been up. So I want to make sure you guys have enough time to deal with this information. All right, so we're going to be talking about common ions today. And we're going to do a bit of review before we do that. And one of the things that I want to talk about is where have we been so far? So we started by talking about chemical equilibrium, right? And I'm actually going to add one of these. So we started by talking about chemical equilibrium. And when we talk about chemical equilibrium, we talked about where does that balance lie. So we're looking at writing a K. We have a number of different Ks that we've written, and it's always some form of products or reactants. Of course, they aren't going to appear if they're solids or liquids, but everything else does appear. We have one that's just for pressure, and that's when we put everything into pressure as opposed to concentration. We can talk about concentration for Kc. We can use concentration in KEQ, which is specifically an equilibrium constant. We've talked about Kw, which is specific to the water reaction. We've talked about Ka in terms of acids. So, sorry, Kw, Ka, Kb, Keq, Kc, Kp. So W is for water, and that's Kw is equal to the H plus times the OH minus. And at 25 degrees, that's equal to 1 times 10 to the minus 14th. Our Ka is for acid. Our Ka is going to be equal to the H plus times the A minus over the concentration of HA, where the reaction that we're looking at is HA dissociating to give us H plus plus A minus. And this applies to any weak acid. If it's a strong acid, that K is not defined because our HA, this concentration down here, doesn't exist. There is no HA, and so therefore Ka is undefined for a strong acid. Kb is for our base, and so the reaction that we're looking at there is going to be that base plus an H2O, giving me a BH plus plus an OH minus. And that base could be anything. So we could be talking about NH3, which is ammonia, CH3, NH2, which is methylamine, any of the things that we have that are bases that can accept protons, okay? Because those are going to be our weak bases, all right? So if they can accept a proton, they are, a Bronsted-Lowry base, they also act as Lewis bases, then they're going to be weak bases that we can talk about in this way. So the Kb for that is going to be equal to that BH plus times the OH minus over the concentration of the base, because the H2O being a liquid does not appear. Okay, so that's not part of it. We can talk about KEQ, and when we talk about KEQ for AA plus B, B going to C, C plus D, D. If A is aqueous, B is a liquid, C is aqueous, D is a solid, then our KEQ is going to be equal to the concentration of C raised to the C power over the concentration of A to the A power, because only those two components will appear because the liquids and the solids do not appear. Again, that's because their concentrations are very large, so they don't appear. Kc specifically is for any reaction, in which case we're using concentrations. Now notice, everything that I've written so far is a concentration. That's what those brackets refer to. We should be looking at something in terms of molarity when we do that. A Kp, on the other hand, is in terms of pressure. And we usually write pressure like Pn2, and then the exponent would be that kind of thing. So that would be for an N2 that has 2 of them. So that pressure is then squared. So in that case, that's going to be in ATMs or other pressure units. We typically use ATM. Okay. So those are some of the Ks that we've talked about. Now we also talked about another one we just talked about, KSP, which is a solubility product. And we know that we had a solid. So I'm going to do AgCl, which is a solid. It is not very soluble. That comes apart to give me an Ag plus a Cl minus, which, yeah, I'm just going to do it that way. And my solubility product for that KSP is going to be equal to the Ag plus times the Cl minus. And of course that solid doesn't appear, so that's all we have for our KSP. Okay. So those are the things that we're typically looking at. Now, in all of the things that we've done, when we've talked about these different things, we've talked about how do we take the information that we have, either initial concentrations, equilibrium concentrations, and put that information into these Ks to solve for other things, right? So we've talked about, all right, I have an initial concentration for an acid. What's the pH going to be at equilibrium? I have equilibrium concentrations for the acid. My pH at equilibrium is, what's the Ka for this? Or what was the initial concentration for this? We can do all of those using Rice tables or ice tables, which we have talked about. We're going to talk about those a bit more today. The purpose of a Rice table or an ice table is to help you categorize the information that you have. So when I talk about these, what I always do, and hopefully what you've picked up on, is that I'm going to write myself a balanced equation. And that's that first part, that R. And so if I write a balanced equation, and if we were to talk about HA coming apart to give us H plus A minus, that's my reaction. We would then have our initial conditions below that. And because we're starting with HA and it hasn't dissolved yet, we always put our initial conditions for our products as 0. And our HA is whatever concentration we started with. So if I started with a 0.25 molar solution, I would put that right there, right? And I assume that these are all moles per liter, so I don't include that unit there. When we talk about our change is always based on the stoichiometry of this reaction, right? So if I break down an HA, every time I break one down, I subtract one, right? Every time I break one down, I get an H plus and an A minus. So I get a plus X and a plus X. And that means that at equilibrium, my equilibrium row is always the sum of the I and the C. So 0.25, and it's minus X because it's a negative. My H is going to be just X, and my A is going to be just X. Now, we make the assumption that the X that we're looking at in terms of the dissolution of HA is very small comparative to our initial concentrations. Now, is that always true? No, but for most of the things that we're going to look at, that's a perfectly fine assumption to make. And if it's not, if you're in a situation where you need to be looking at that, then that's something you're going to have to deal with, in terms of doing that math and working with the quadratic, and it's going to be slightly more complicated, okay? But that's the assumption that we make. So when we do that, that allows us to then say, okay, well, the Ka for this is then that H plus times the A minus over that HA, and my Ka is going to be equal to X times X over the initial concentration of HA. So here, 0.25. And if I knew which acid I was talking about, rather than being a generic HA, if I was talking about, say, acetic acid, then I could take my lovely chem handouts. Oh, you can't see that. Oh, dear God. Okay, there we go. So the exam handouts that you're going to have, and I could open this up to the back of this. So on page 10, you'll see that there are ionization constants for some weak bases and some weak acids. There are also some for diprotic acids and polyprotic acids. That's all on page 10. We also have a list on page 6 of strong acids and strong bases. So one of the things that I've said is if it's not in that list of strong acids or strong bases, it is weak. Okay, so if it doesn't exist on page 6, it's a weak acid or a weak base, depending on what we're looking at. And it may or may not appear on page 10. But if it doesn't, that doesn't mean it's not weak. Okay, so that's this. The stuff that we have on page 10 is not conclusive for everything that we talk that there is. It's just that these are some examples. Now, if I knew which acid I was talking about, like if I was talking about formic acid, which is HCOOH, right? Then this would then be HCOOH. We'd have an H plus there and an HCOO minus. Okay? So that's what we would be looking at in those terms. Now, when we talk about that, we can then talk about that K value for that formic acid. Ka is equal to 1.7 times 10 to the minus 4th. And I got that value from the table on page 10. So the table on page 10, which I know you can't see very well because it's purple, has Ka values in it. All right. So I can use those values to do this. Now, it is my expectation that when you're taking the test that you will have those handouts available to you because sometimes that information is in there. It's also very helpful to you if you've learned to, okay, strong acids are here. I can go check that. If it's not in that list, then it must be weak. So therefore it's going to be these things. That's important. Okay, so that is part of the expectation. Now, once I have that Ka, then I know that I can set that Ka, 1.7 times 10 to the minus 4th, equal to x squared over the initial concentration. So I take that 1.7 times 10 to the minus 4th, I multiply it by my initial concentration, and that's equal to x squared. I can then solve for x, and I don't have my calculator. Give me a second because I need it. I apologize, I do this all the time. Trust me, I do this in class too. And I always forget that I need this thing. So 1.7 times 10 to the minus 4th. And when I enter that again, it's 1.7 second E minus 4. And the reason that we have to do it that way when we do the scientific notation, if we enter it as 1.7 times 10 exponent negative 4, and we do a bunch of calculations, including those, times 10 to the whatever, then we end up with powers of 10 problems. So they're either going to be too big or too small based on a power of 10. So we need to make sure that when we're doing scientific notation, we use the second EE, because that's what scientific notation is on your calculator. So I take the 1.7 EE to the negative 4 times the 0.25. That gives me 4.25 times 10 to the minus 5th. I can then take the square root of both sides to get x equal to a second square root, second answer. And I get 0.0065. Now, that number goes right there. Okay, so that's the concentration of H plus and the concentration of A minus in this case. We can also find the concentration of HA that is left by 0.25 minus this 0.0065. And that gives me 0.243, okay? And you can see that that's not really that different. Now, is it different enough? Well, that depends on how you want to talk about it. I don't think that it is, given that we're only looking at 2 sig figs, that's really not that big a deal, okay? So there are ways that we can deal with that. Now, I did all of that because I want to remind you that we write the balanced equation, we set up our ice table, we include anything that we were given, and then find the rest of it. So if I were given this concentration at equilibrium, the one right here, if I had this value, then I could take and solve for Ka. So I could find Ka if I know my equilibrium concentrations. If I find Ka for a certain temperature, then I can use it for other other concentrations to solve for things. We can do that. So we can find those relationships. There's lots of math that we can do with all of this stuff. One of the reasons that we have to talk about that is because today we're going to be talking about something called the common ion effect. So let's talk about common ions and see what they are, and then we'll see how that relates into this math. Okay? So that's our goal. But let us review a tiny bit more before we do that. So, write a molecular, ionic, or net ionic equation for the formation of MgOH2 from MgNO3 and KOH. So I know I'm taking MgNO3 I'm reacting that with KOH. That's going to give me an MgOH2. And I know that MgOH2 is a solid because I know it's not soluble, which I know from the solubility rules that happen to be in here. Yay, I can look at those to see that that's not soluble. Awesome. So this is the reaction that I need to deal with. Now, is that my only product? No, it's not. And I know that it's not because if I look at what I have here, I have an Mg that's on the reactant side. So Mg that's on the reactant side, and I have an Mg on the product side. I have an OH on the reactant side. I have two OHs on my product side. I have no potassium on my product side, and I have no NO3 on my product side. So I know I'm not done yet. Okay. So in order for me to do this, I took the cation from the first one, so the Mg from the first species, and I paired it with the product from the second one. And of course, the Mg is a 2+, and I know it's a 2+ because NO3 is a -1. So since I have two of the NO3s, that means Mg must be a 2+. It is an alkaline earth metal, so I would expect it to be a 2+. And that's why I need two of the OHs here. So that means that I need to then have two OHs on my reactant side. So I multiply that times 2. That means I then have K, and that reacts with the NO3. So the other cation and the other anion come together. K is +1 and NO3 is -1. So that's how that balances. But I need to have two of those because I need to have two Ks on both sides. So now I have one Mg on reactant side. I'll show you what I'm doing. One on each side. I have an NO3. I have 2 and 2. I have K, 2 and 2. And I have OH. And I'm not going to put the charge on it. I'm not putting any of the charges on. I have 2 and I have 2. So I know that I'm completely balanced when I do that. I'm going to erase that because what I need to look at now is the rest of what I've got here. And so what kind of equation did I just write? Well, I wrote something called a molecular equation. And it's a molecular equation because I have everything written as molecules. Even though I know that 3 of these species are aqueous. And so they're actually in solution, dissolved. And so they're disassociated, which means I have an Mg2 plus 2 NO3 minus plus 2 K plus 2 OH minus. That goes to give me an MgOH2 solid, which stays together. It does not come apart because it's a solid. Plus 2K plus 2 NO3 minus. And this is my molecular. This is my ionic. And in that case, I have all of the ions that are present. But I know that something has gone through a change. So I've formed a solid. And that solid is in a different phase. Excuse me, sorry. And so that's interesting chemistry to me as a chemist. So I might be interested in how did I make that solid? Well, I made it from the Mg2 plus, which is aqueous, plus the 2 OH minus that are aqueous, giving me an MgOH2 solid. So that's my net ionic equation. I have taken all of this stuff that didn't do anything and taken it out. So they're just standing around watching the bar fight. I don't give a crap that they're standing there. I need them out of my way. I need to be looking at who was involved in the fight, because those are the people that I need to interview, because, I'm a cop in this cute little scenario. So that's what we're dealing with there. Okay, so this is my net ionic. Now, notice I said or. So you could have written any of those. Any one of them would have been fine. But for illustrative purposes, I did all three. Okay? So those are my balanced equations. And I need those to be able to deal with my KSPs. Okay, awesome. What's next? Write a KSP expression for the following solids. So I have copper sulfide. That copper sulfide solid comes apart, becomes a Cu2 plus an S2 minus. Both of those are aqueous. That means the KSP is equal to that Cu2 plus times the S2 minus. Okay, awesome. That was fun. When we talk about the chromium hydroxide, CrOH3, that comes apart to give me a Cr3 plus aqueous plus 3OH minus aqueous. And that means that KSP is equal to that Cr3 plus times the OH minus cubed, because there are three of them. So we need to have that cubed. Okay, awesome. Let's talk about our Mg3PO4. Well, Mg3PO4 comes apart to give me 3Mg2 plus, which is aqueous, plus 2PO43 minus, which is aqueous. And the KSP for that is going to be equal to Mg2 plus, that ion, cubed, because there are three of them, the PO43 minus, that ion, squared, because there are two of them. So that's my KSP for that thing. There are lots of ions there, so we end up with a big expression. Okay? Let's talk about our PbCl2. PbCl2 is a solid that comes apart to give me a Pb2 plus a Cl minus, or two Cl minuses, because I have two of them. My KSP is then equal to the Pb2 plus times the Cl minus squared. And our last one, Bi2S3 is a solid. It comes apart and it gives me a Bi3 plus and an S2 minus. Now I know that S is 2 minus, so that's how I know that the Bi is 3 plus, because we end up with 3 S's and 2 Bi's, and that gives me a total of 6 as my charge. Both of these are aqueous, and that means my KSP is going to be equal to the Bi3 plus times the S2 minus. So that's my expression there. Well, awesome, that was fun. So again, just those products, but we need to make sure that we've got the correct number of those products. So we need to make sure that we've balanced for charge. So if I was to say the bismuth sulfide, and I didn't have Bi2S3, then that KSP would be totally messed up, right? And of course, is it correct the way I wrote it? And actually it's not, because I have Bi3 plus, but I don't have two of them. I have S2 minus, but I don't have three of those. So the Bi2 3 plus over here should be squared, and that one should be cubed. And that's what we mean about making sure that we have the stoichiometry correct. Because if I don't, then my exponents are totally wrong. We need to make sure that we've paid attention to them. Okay? That's what we're talking about. Cool. Awesome. That was fun. Let's talk about our next one. Calculate the solubility of each of the following materials in pure water, given the KSP values. So CrOH3 has a KSP of 3.0 times 10 to the minus 29. Okay, fine. I will start with a balanced equation. CrOH decomposes to give me a Cr3 plus 3 OH minus. We actually wrote this previously. We can then set up our ice table for this. And of course, it's going to be really tiny. So my I, do I have any? No. And of course, this is solid, so I don't care about that. I don't start with any of the chromine. I don't start with any of the hydroxide. My change is going to be a plus X here plus a 3X there. And that means that my equilibrium rho is going to be equal to X and 3X. Okay. In order to find that, I need to find KSP is equal to the Cr3 plus times the OH minus cubed. I know that Cr3 plus is an X, the OH minus is 3X, and that has to be cubed. So I've taken that thing that I put in that change row, and I've plugged it in as the concentration of that species. So whatever power that concentration is raised to, I have to raise that X term to as well. So that's why we have that 3X, and the whole thing is cubed. And when I do that, that means that I end up with X times 3 times 3 is 9. 9 times 3 is 27. 27x cubed, which then gives me 27x to the 4th as my final thing that I have there. And I know that this thing is equal to 3.0 times 10 to the minus 29 because that's what it said that the KSP value was. So that's my lovely expression. So I can take my 3.0 times 10 to the negative 29. I can then divide that by 27. That gives me x to the 4th is equal to 1.1 times 10 to the negative 30th. I then take that to the 4th root. So I take the 4th root of this, which is the 1/4 power. So on my calculator, I hit the little hat symbol, so that thing, and then I do parentheses 1 divided by 4, hat, parentheses 1 divided by 4, and that gives me x is equal to 3.2 times 10 minus 8, 2 sig figs. Sorry, 3.2, and I was checking to see if I needed to round up, but I didn't. Okay, so that's my x value. So that is my Cr3 plus. My OH minus, on the other hand, is going to be that 3.2 times 10 to the minus 8 times 3, which gives me 9.7 times 10 to the minus 8th. Okay, so that's both of those concentrations at equilibrium. Awesome. That's exciting. Now, when it says solubility, there are two things that it's looking for. So either you're looking for the molar solubility, which is this number, the X. The X is always the molar solubility. So this is the molar solubility. This is how many moles per liter will dissolve. Okay. The other thing we can talk about is grams per liter. Okay. So in order to find the grams per liter, I would need to take that 3.2 times 10 to the minus 8 moles per liter and multiply that by the molecular weights of the CrOH3. Now, I'm going to cheat when I do this, and I'll show you what I mean by cheating. I have an internet page that I use when I do this. So I'm pulling this up. This is the Linentech. And you come in here, CR. You can see that I've done this before, and I typed it wrong. So CrOH3. And of course it doesn't like that, and it doesn't like that because the capitalization's wrong. So it needs to be a C, big C, little r, and then OH3. Okay. It finds the molar mass of the Cr, of the H, and of the O, and multiplies them by the number that is present, and then gives me the total 103.02. So I would multiply this answer by 103.02 3.02 grams per mole. And that would then give me the solubility in grams per mole. So 3.2 times 10 to the minus 8, the molar solubility that I found, times 103.02, and that gives me 3.3 times 10 to the minus 6. Really, that's a 6 grams per liter. And that's for that CrOH3. Okay, awesome possum. So that's what we were talking about for that. Now, if I want to talk about this other one, this PbCl2, I'm going to start in the same way. PbCl2 is a solid. It becomes a Pb2 plus 2 Cl minus. I know that that is going to be my setup for a rice table. And I'm not going to put the R, but I know that it's there and implied. We didn't always refer to them as rice tables. Some people still refer to them as ice tables. But I found that I always have to write the reaction first to make it work. So why not just call it a rice table? First time I saw it, I was very offended by it and I wouldn't do it because I was used to it as an ice table. But now I understand why people do that. Okay, I don't care. Use whatever you want. So this is the solubility I'm looking at. I don't care about that PbCl2 because it's a solid. So it does not appear, it is not important. But I know that I start with an initial solubility of Pb of 0 and the Cl is 0 as well. That means that every time I break down a PbCl2, I get a Pb and I get 2 Cls. That's based on the stoichiometry. And then that means that at equilibrium, this is going to be x. This is going to be 2x. So if my Ksp is equal to the concentration of Pb2 plus times the concentration of Cl minus squared, then this is going to be an x. That's going to be a 2x, and that entire thing is squared. Okay. I also know that that's equal to 2.4 times 10 to the minus 4th, because that's what they told me above. It said that the Ksp is 2.4 times 10 to the minus 4th, which is right here in and amongst all of my scribbling. Okay, so that means, again, I have to square both the 2 and the x. So that gives me 4x squared times x is equal to 2.4 times 10 to the minus 4th. We then end up, 4x cubed, because x times 4x squared is 4x cubed, 2.4 times 10 to the minus 4th. I'm going to divide both sides by 4. 2.4, second EE minus 4, divided by 4, and it gives me x cubed is equal to 6 times 10 to the minus 5th. I take the cube root of both sides, cubed, so there's second math. Oh, that's all I wanted. Second math. Oh, damn it, just math. And then the fourth one down on my calculator is cube root. And then second answer. And that gives me x equals 0.039. I take that value and I can put that right here, 0.039. And of course, my chlorine is going to be twice that because of the 2. 0.078 is what I get for that one. So those are the two values that I was looking for there. Now, my molar solubility is always the x value that I solved for. So that's this right here. And that's in moles per liter. If I wanted to solve for it in grams per liter, I would multiply this by the molecular weight of PbCl2, which I can find. Where did I put my... PbCl2, which is 278.11 grams per mole, and that gives me 10.89 grams per liter is my solubility in grams per liter. Now, the question asked for solubility. There was nothing specific about whether it wanted molar solubility or grams per liter. That is entirely up to you then. If it doesn't specifically state, you can give me either answer because they are both correct. So either one of those would work. And the only reason I did them both is so that you can see the math that's involved in both of those calculations. Okay? So I hope that there are no questions from that. If there are, you know how to reach me. That is the end of our review. So I'll stop this section and get ready for our next one. Thanks, guys.